So in this example, we're given this circuit here. It does have a independent current source, but then a dependent voltage source. And we're asked to find the Norton equivalent circuit between terminals A and B. Now we'll recall that a Norton equivalent circuit is a circuit with a current source in parallel with a resistor that could be placed in place of the circuit between the terminals A and B that would function the same. And this current here would be the short circuit current, and this is the Thevenin resistance here. So let's see what we need to do to accomplish this. So the first thing we want to do is we look at, from these 2 points here, looking this way, we have a current source in parallel with a resistor. And so with that, we can do a source transformation, which means when we have a current source in parallel with a resistor, we can place that with a voltage source in series with the resistor. And when we do that, the resistor stays the same, and the voltage source is just the current times the resistance. So in this case, it would be 2 times 10, which would be 20 volts. So we can replace everything to the left of these 2 points with that. So let's do that real quick, and I think that will simplify our circuit just a bit. So if we do that, that would replace all of this. So we will replace that and this. And so what we would have now would be that same resistor, which we said was 2 ohms, and it'll be in series with this voltage source, which we said would now be 20 volts. So this simplifies our circuit a little bit, makes it a little easier to analyze. So first thing we want to do is we want to do a KVL, or a voltage loop analysis of this, and we're going to go around in this direction when we do that. And so when we do, let's look and see what we have. So the first thing we have is our 20 volt, source. And because we have the negative sign first, that's going to be a negative 20. And then as we come around, we hit the 2 ohm resistor, and we see that we've already got the current defined as I1. So this I1 is going to go through our entire loop. So that being the case, as we look at our 2 ohm resistor, that's going to be plus 2 times I1. And then we come across a voltage source, which is defined. It's a current-controlled dependent voltage source. And so we see we hit the negative sign first. So let's identify this. So this is our voltage source. And so it's going to be, the voltage is going to be minus 2I1. And then finally, as we come down through this resistor here, we'll define that with this color. That's going to be plus 6I1. And that closes our loop, so then we should be able to set that all equal to 0. And so in this case, we have one equation with one unknown. And so as we combine like terms and divide things out, we should see that we have I1 is equal to 20 over 6. And so this is going to be 10 over 3 amps. And we also note that the voltage across AB, VAB, is going to also be equal to our open circuit voltage. So in that case, our open circuit voltage is equal to VAB, but from Ohm's law, we know that that's IR, and so that's 6 times I1. Well, we just solved for I1, and so that's going to be 6 times 10 over 3, and so that's going to be 20 volts. So our open circuit voltage, and we'll just tabulate this over here, open circuit voltage is 20 volts. So now we need to figure out what the short circuit current would be. And so that would be, if we were to short this out, put a wire here and short it out, what current's going to flow here? And that's going to be our ISC. And that's what's going to be part of our Thevenin circuit. So to do that, we want to do a node analysis. So let's start our colors over here again. So we're going to be looking at this node here, and we're defining current leaving the node as positive. So when we do that, we've already have the purple, so we'll just keep the same colors going here. So our 6 ohm resistor is in the purple, so the current through there is going to be V over 6. And then we'll do another color here. We'll just say green for the 3 ohm resistor right here. And so we'll just use that color green. And so that's going to be plus V over 3. It's the same voltage. All right, and then so that leaves our last leg, which is, and we'll go back to our red. That's this leg here going in this direction. And so when we do that, we get, we'll do this in red, plus, sorry, it's going to be plus V minus 2 I1, so that's that voltage source, minus 20, that's our independent voltage source, over the 2 ohms. And so again, that should all equal to 0. And we also keep in mind that I1 is equal to V over 6. So with that, we can rewrite this then, multiplying through by 6 is V plus 2V plus 3V minus 6I1 minus 60. And that should all equal to 0. So then we'll have 6V minus 6 times V over 6 is equal to 60, or 5V equals to 60. V should be 12 volts. So that being the case, our short circuit then is going to be V, that voltage across A and B, or that voltage across the resistor, divided by 3 ohms. That's this resistor here. So that'll give us the current flowing in this leg. And so that's 4 amps. So our ISC is equal to 4 amps. And then finally, our Thevenin, let's do that here. Our Thevenin resistance is defined as our open circuit voltage over our short circuit current. And so we know that's 20 over 4. And so that's 5 ohms. So now, finally, we come back to our Thevenin equivalent circuit. So we'll have this current source here in parallel with the resistor. And again, this will be terminals A and B. And our short circuit current is 4 amps, and our Thevenin resistance is 5 ohms. So this is our Thevenin Norton equivalent circuit for the circuit given in the problem.